What if I told you that the force holding you to your chair right now, the same force keeping planets in orbit around stars, might not follow the rules we thought it did? What if gravity itself operates according to principles so fundamentally random that they could make the weight of objects unpredictable, challenging even some of our most basic measurements? Recent groundbreaking research suggests this isn't science fiction, but a deeply unconventional possibility that challenges everything we understand about the nature of reality. Welcome back to another journey into the mysteries that shape our existence. I'm here to guide you through one of the most unsettling discoveries in modern physics, a theory so radical that leading scientists have placed a 5,000 to 1 bet against its validity. Today, we're exploring whether gravity might be random rather than quantum, and why the evidence supporting this idea could fundamentally reshape our understanding of the universe itself. Before we begin this exploration together, take a moment to settle in. Whether you're listening during a quiet evening walk, curled up in your favourite chair, or letting these ideas wash over you as you drift towards sleep, know that what we're about to discuss will challenge some of your deepest assumptions about how reality works. The implications are so profound that they've divided the physics community and sparked debates that could define the next century of scientific inquiry. For over a century, physicists have lived with an uncomfortable truth. The two pillars supporting our understanding of the universe, quantum mechanics and Einstein's theory of general relativity, are fundamentally incompatible. It's as if the universe operates according to two completely different sets of rules, depending on whether you're looking at the smallest particles or the largest structures in space. Quantum mechanics governs the realm of atoms, electrons, and photons with extraordinary precision. It tells us that particles can exist in multiple states simultaneously, that they can be entangled across vast distances, and that the very act of observation changes their behaviour. This theory has given us lasers, computers, and medical imaging technologies that seemed impossible just decades ago. General relativity, on the other hand, describes gravity not as a force but as the curvature of spacetime itself. Massive objects like stars and planets bend the fabric of space and time, creating what we experience as gravitational attraction. This theory has been confirmed by countless observations, from the precession of Mercury's orbit to the detection of gravitational waves from colliding black holes. The problem is that these theories make contradictory predictions about what should happen at the intersection of the very small and the very massive. Black holes, for instance, are objects where quantum effects should be important, but where gravity dominates. The mathematics of the two theories simply cannot be reconciled in these extreme environments. For decades, most physicists have assumed that the solution lies in quantizing gravity, making it conform to the strange rules of the quantum world. This approach has led to elaborate theories like string theory, which requires the existence of multiple extra dimensions, and loop quantum gravity, which suggests that space itself is made of tiny discrete units. But what if we've been approaching this problem backward? What if instead of making gravity quantum, we need to accept that gravity operates according to fundamentally different principles? This is the revolutionary proposal that has emerged from the work of Professor Jonathan Oppenheim at University College London, and it's sending shockwaves through the physics community. Oppenheim's theory, called post-quantum gravity, represents a radical departure from conventional thinking. Instead of trying to squeeze gravity into the quantum framework, it proposes that gravity remains classical, but with a twist so unconventional that many physicists refuse to accept it. According to this theory, space-time itself is subject to random fluctuations that make the universe less predictable than previously assumed. Think about what this means for a moment. In our everyday experience, we take for granted that objects have stable, measurable properties. A kilogram of mass weighs exactly 1 kilogram, regardless of when or how many times we measure it. But Oppenheim's theory suggests that if we could measure precisely enough, we would find that the weight of objects could subtly fluctuate over time due to chaotic disturbances in the fabric of space-time itself. These aren't small theoretical fluctuations that only matter in abstract calculations. The theory predicts that these random variations in space-time are larger than what quantum mechanics would allow, potentially making even macroscopic measurements fundamentally uncertain. The kilogram mass that serves as an international standard in France might literally become heavier or lighter from moment to moment, not because of any external influence, but because space-time itself is writhing with random energy. The philosophical implications are staggering. For centuries, science has been built on the assumption that the universe operates according to deterministic laws. Even quantum mechanics, despite its probabilistic nature, follows precise mathematical rules that allow us to calculate the likelihood of different outcomes. But Oppenheim's theory suggests that randomness is woven into the very structure of reality at the deepest level. Einstein famously declared that God does not play dice with the universe, expressing his discomfort with the probabilistic nature of quantum mechanics. If Oppenheim is correct, not only does God play dice, but the dice themselves are constantly changing in unpredictable ways. The universe becomes not just probabilistic, but more variable in ways that challenge classical expectations, with outcomes that cannot be predicted even in principle. As you contemplate this idea, notice how it might challenge your own assumptions about the nature of existence. We've grown accustomed to thinking of the physical world as stable and reliable, the foundation upon which we build our understanding of everything else. But what if that foundation is actually shifting beneath our feet in ways we cannot see or predict? One of the most compelling pieces of evidence for Oppenheim's theory comes from reconsidering one of physics' most famous experiments, the double-slit experiment. In this demonstration of quantum weirdness, individual particles such as electrons or photons are fired at a barrier with two narrow openings. Despite being sent one at a time, these particles create an interference pattern on a detector screen, as if each particle somehow passes through both slits simultaneously and interferes with itself. This experiment has long been held up as proof that quantum mechanics accurately describes reality at the smallest scales. But it also creates a problem for any classical theory of gravity. If gravity were purely classical and deterministic, it should theoretically be possible to determine which slit a particle passes through by measuring its gravitational field with sufficient precision. Making such a measurement would destroy the interference pattern, even if the measurement were never actually performed, simply because the information would exist in principle. Since we do observe interference patterns in laboratory experiments, this seemed to rule out classical gravity entirely. The particles must somehow pass through both slits in a quantum superposition, immune to gravitational measurement. This logic has driven physicists toward quantum theories of gravity for decades, but Oppenheim's theory offers an unexpected resolution. If gravitational fields themselves fluctuate randomly, then it becomes impossible to determine which slit a particle passed through, even in principle. The randomness in spacetime provides a kind of cosmic noise that masks the particle's path, preserving the interference pattern while allowing gravity to remain classical. This solution is both elegant and deeply counterintuitive. It saves the classical nature of gravity, but only by introducing fundamental randomness into the gravitational field itself. The price of resolving this paradox is accepting that space-time operates according to less predictable principles that make precise gravitational measurements impossible, not because of technical limitations, but because of the inherently random nature of the gravitational field. The implications extend far beyond laboratory experiments. Every object in the universe, from subatomic particles to massive stars, would be subject to these random gravitational fluctuations. The orbits of planets, the behavior of galaxies, and the evolution of the universe itself would all contain elements of unpredictability. Some of the most intriguing support for these ideas comes from an unexpected source: the IceCube Neutrino Observatory, buried deep in the Antarctic ice. This extraordinary facility detects neutrinos, nearly massless particles that can travel billions of light years through space without interacting with matter. Because neutrinos are affected only by the weak nuclear force and gravity, they serve as pristine messengers from the most distant corners of the universe. Researchers have used IceCube to search for signs that space-time itself exhibits quantum behavior. If gravity were truly quantum, the passage of neutrinos through quantum fluctuations in space-time should leave subtle signatures in their properties. By studying over 300,000 neutrinos that have travelled across cosmic distances, scientists have looked for evidence of quantum gravitational effects. The results are both fascinating and scientifically surprising. No evidence of quantum gravitational effects has been found, despite the experiment's extraordinary sensitivity. The constraints placed on quantum gravity theories are now over 1 million times stronger than previous limits. This absence of evidence doesn't prove that gravity isn't quantum, but it does suggest that if quantum effects exist, they are far smaller than many theories predict. This null result lends indirect support to theories like Oppenheim's that propose gravity might remain classical. If space-time doesn't exhibit quantum behavior on the scales that these sensitive experiments can probe, perhaps we need to seriously consider alternatives to quantum gravity. The neutrinos having travelled for billions of years through space that might be fundamentally classical rather than quantum, arrive at Earth carrying this profound message about the nature of reality itself. Take a moment to consider the implications of this cosmic experiment. Particles that began their journey when the universe was young have travelled across unimaginable distances to reach detectors buried beneath miles of ice. The fact that they show no signs of quantum gravitational effects suggests that the vast emptiness of space might operate according to principles fundamentally different from what we've assumed. Perhaps the most immediately striking prediction of Oppenheim's theory concerns something as basic as weight. The theory suggests that if we could measure the mass of objects with sufficient precision, we would find that their apparent weight might subtly fluctuate over time. This isn't a measurement error or instrumental limitation, but a proposed property of space-time itself. The International Bureau of Weights and Measures in France routinely weighs a 1 kilogram mass that once served as the international standard for the kilogram. According to Oppenheim's theory, if these measurements were precise enough, they would reveal tiny but real fluctuations in the mass's apparent weight. These variations would be caused by random disturbances in space-time that affect how matter interacts with the gravitational field. The experimental test is elegantly simple in concept but revolutionary in its implications. If the predicted fluctuations are observed, it would confirm that space-time operates according to fundamentally random principles, If the fluctuations are smaller than the theory requires, the theory can be ruled out. Either outcome would be scientifically significant, but a positive result would transform our understanding of reality itself. Consider what this means for our most basic assumptions about the physical world. We expect that identical objects should have identical weights, that measurements should be reproducible, and that the physical properties of matter should remain constant over time. But if space-time itself is subject to random fluctuations, then even these fundamental expectations might be wrong. The implications extend far beyond scientific measurements to touch on practical questions about technology and engineering. Precision instruments that rely on exact masses or distances might be fundamentally limited not by technical imperfections, but by the potential variability of space-time itself. Navigation systems, atomic clocks, and gravitational wave detectors might all be subject to random errors that cannot be eliminated through improved design. As you reflect on these possibilities, consider how they might change your relationship with the physical world around you, the solid objects that surround you, the ground beneath your feet. Even your own body might be subject to tiny but real fluctuations that make their properties fundamentally uncertain. This uncertainty isn't a limitation of our knowledge, but could be a basic feature of reality itself. One of the most intriguing aspects of theories involving space-time fluctuations is their potential connection to one of cosmology's greatest mysteries: dark matter. This invisible substance is thought to make up about 85% of all matter in the universe, yet it has never been directly detected despite decades of increasingly sophisticated searches. Some theoretical approaches suggest that what we interpret as evidence for dark matter might actually be the result of random fluctuations in space-time itself. According to these ideas, the anomalous behaviour of stars in the outer regions of galaxies, which led astronomers to propose dark matter in the first place, could be explained by the cumulative effects of space-time fluctuations rather than invisible particles. The energy that keeps stars moving at unexpected speeds in galactic outskirts might come from random fluctuations in the fabric of space and time. These effects would be strongest where gravity is weakest, precisely the regions where dark matter's influence is most apparent. If confirmed, this would mean that one of the universe's greatest mysteries might be solved not by discovering exotic particles, but by recognizing the potentially complex behavior of space-time itself. This possibility is both thrilling and profoundly surprising. On one hand, it would resolve the dark matter puzzle without requiring new types of matter that interact only gravitationally. The universe would be simpler, in some sense, containing only the ordinary matter and energy we can observe directly. On the other hand, it would mean that the large-scale structure of the universe is governed by processes that make cosmic evolution less predictable. Imagine galaxies as islands in a dynamic sea of space-time fluctuations, their motion influenced not only by the gravitational pull of visible matter, but also by invisible waves of random energy that surge and ebb according to no discernible pattern. The stately rotation of spiral galaxies, the collision of galaxy clusters, and the formation of cosmic structure itself would all contain elements of deep complexity. The implications for our understanding of cosmic evolution are profound. If space-time fluctuations play a significant role in shaping the universe, then the history of cosmic development might contain crucial random elements that make it impossible to fully explain why the universe looks the way it does. The formation of galaxies, stars, and ultimately life itself might depend partly on chance events that occurred in the chaotic quantum foam of early spacetime. The revolutionary nature of these ideas has created an unprecedented situation in the normally staid world of academic physics. Professor Oppenheim has entered into a formal bet with Carlo Rovelli, a leading proponent of loop quantum gravity, and Jeff Pennington, a prominent string theorist. The stakes are significant, 5,000 to 1 odds against Oppenheim's theory being correct. This bet represents more than academic wagering. It reflects the profound uncertainty that exists at the highest levels of theoretical physics about fundamental questions that most people assume have been settled. The extreme odds reflect both the radical nature of Oppenheim's proposal and the confidence that establishment physicists have in existing quantum gravity approaches. But the very existence of such a bet also reveals something deeper about the current state of physics. After more than a century of effort, we still don't understand how gravity relates to the other fundamental forces. Theories that were supposed to provide a unified description of nature remain untested and perhaps untestable. The bet acknowledges that we might be facing a genuine conceptual crossroads in our understanding of reality. The proposed experimental test is deceptively simple. Measure a mass with extraordinary precision to see if its weight fluctuates over time. If the fluctuations are detected and match the theory's predictions, Oppenheim wins and physics faces a conceptual revolution. If the fluctuations are smaller than predicted, the theory is ruled out, and physicists must continue searching for other approaches to unifying gravity with quantum mechanics. Either outcome would be scientifically significant, but a positive result would be truly transformative. It would suggest that the universe operates according to deeply unconventional principles at its most fundamental level, making certain types of knowledge impossible in principle rather than just practically difficult to obtain. As we contemplate these ideas, we're witnessing science at its most adventurous and uncertain. The questions being explored touch on the very nature of reality, the limits of knowledge, and humanity's place in a universe that might be far stranger than we've imagined. The answers, when they come, will shape not just physics but our entire worldview for generations to come. In our next exploration, we'll delve deeper into the challenging implications of a fundamentally random universe, examining how quantum information might behave in black holes and what this could mean for the nature of memory, consciousness, and the permanent record of existence itself. The most unsettling prediction emerging from this new understanding of gravity doesn't concern measurements in earthly laboratories or the behavior of distant galaxies. It touches on something far more fundamental and deeply personal: the possibility that information itself can be fundamentally altered, not hidden, not transformed, but potentially lost in ways that challenge everything quantum mechanics has taught us about the conservation of information. In the realm of black holes, where space-time curves so severely that not even light can escape, Oppenheim's theory makes a prediction that many physicists find genuinely disturbing. Unlike quantum theories of gravity, which insist that information falling into a black hole must somehow be preserved, this post-quantum approach suggests that black holes might allow information to behave in ways that appear non-conserving. Consider what this means on a personal level. Every thought you've ever had, every memory you've formed, every moment of consciousness you've experienced exists as patterns of information encoded in the neural networks of your brain. These patterns are made of atoms, and those atoms obey the laws of physics. In a quantum universe, the information content of these patterns would be conserved eternally, perhaps scattered and transformed beyond recognition, but never truly lost. But if Oppenheim's theory is correct, and if that information were ever to fall into a black hole, it could be altered in ways that defy standard expectations. Your memories, your experiences, your very essence as an information processing system might not be preserved, not just from practical access, but from the universe's broader informational structure. The black hole wouldn't just hide this information behind an event horizon. It could transform or eliminate it in ways still not fully understood, leaving no trace that it ever existed. This isn't merely a theoretical concern about distant cosmic objects. As you listen to these words, processing them into memories and connecting them with your existing knowledge, you're creating new patterns of information. In a universe where information can be fundamentally changed, these patterns have a fundamental fragility that goes beyond the biological mortality of your brain. They exist in a reality where permanence itself might be more limited than once assumed. The philosophical implications ripple outward like waves from a stone dropped into still water. If information can be fundamentally altered, what does this say about the meaning and significance of existence? Religious and spiritual traditions often find comfort in the idea that something permanent underlies the temporary nature of physical life. But a universe where information might not always remain intact challenges even these deepest sources of meaning. Scientists have debated the black hole information paradox for decades, trying to reconcile the apparent loss of information in black holes with quantum mechanics' insistence that information must be conserved. Elaborate theories have been proposed involving holographic principles, firewalls, and information storage on black hole surfaces. All of these approaches share a common assumption: information simply cannot be destroyed. Oppenheim's theory cuts through this complexity with a solution as elegant as it is radically different. Information might not always be preserved, and black holes could act as cosmic erasers in some interpretations, removing patterns from existence with striking efficiency. This resolves the paradox by relaxing one of quantum mechanics' most fundamental principles, but it does so by making the universe a far less permanent place than we might hope. As we drift deeper into these implications, we encounter another area where Oppenheim's theory offers solutions that are both satisfying and deeply unsettling. One of quantum mechanics' most persistent mysteries is the measurement problem, the question of how and why quantum superpositions collapse into definite states when observed. In standard quantum mechanics, particles exist in superpositions of multiple states simultaneously until something measures them. An electron can spin both up and down at the same time. A photon can travel through multiple paths simultaneously, and Schrödinger's famous cat can be both alive and dead. But the moment we observe these systems, the superposition collapses and we see only one definite outcome. This process has puzzled physicists for nearly a century because quantum mechanics provides no clear mechanism for why or how this collapse occurs. The theory simply postulates that measurements cause collapse without explaining what constitutes a measurement or why the universe should behave this way. It's as if the mathematical formalism of quantum mechanics is incomplete, requiring an additional rule that seems arbitrary and mysterious. Various interpretations have been proposed to resolve this puzzle. Some suggest that consciousness plays a role in collapse. Others propose that the universe splits into multiple branches where every possible outcome occurs. But these solutions often raise more questions than they answer, leading to philosophical debates that seem increasingly disconnected from experimental reality. Oppenheim's theory offers a radically different solution. quantum superpositions collapse naturally through their interaction with the randomly fluctuating spacetime. There's no need for conscious observers, special measurement devices, or splitting universes. The chaotic nature of spacetime itself provides the mechanism that transforms quantum possibilities into classical realities. This is both elegant and deeply surprising. It removes the mystery from quantum measurement by making spacetime the agent of collapse, but it does so by making randomness fundamental to the structure of reality itself. The universe doesn't need conscious observers to collapse wave functions because spacetime is constantly jittering with random energy that forces quantum systems to choose definite states. In this view, the solid classical world we experience emerges from the marriage of quantum possibilities and chaotic spacetime. Your ability to perceive definite objects with specific properties doesn't depend on your consciousness or some mysterious measurement process. It depends on the interaction between quantum systems and a dynamically fluctuating spacetime field that surrounds and permeates everything in the universe. Take a moment to contemplate your immediate surroundings. The chair you're sitting in, the device you're using to listen to these words, the air you're breathing. All of these exist in definite states, not because they were measured by conscious observers, but because they're constantly interacting with a space-time that fluctuates chaotically at levels too small to detect directly. The implications of these ideas extend into one of modern physics' most spectacular success stories: the detection of gravitational waves. These ripples in space-time, caused by colliding black holes and neutron stars billions of light years away, represent one of Einstein's most profound predictions, confirmed through extraordinary experimental achievement. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, detects these cosmic events by measuring incredibly tiny changes in the length of laser beams traveling between mirrors, separated by several kilometers. When a gravitational wave passes through Earth, it stretches and compresses space itself, causing these distances to change by amounts smaller than 1,000th the width of a proton. But if space-time is subject to random fluctuations, as Oppenheim's theory suggests, then LIGO's measurements might be contaminated by noise that has nothing to do with distant cosmic collisions. The detectors might be constantly bombarded by random variations in the gravitational field that could mask genuine signals or create false detections. Recent theoretical work suggests that dark matter, if it consists of ultralight particles, could create its own fluctuations in spacetime that would appear as noise in gravitational wave detectors. These fluctuations would be like waves in an invisible ocean, constantly jostling the mirrors and introducing uncertainty into measurements that we thought were limited only by technical precision. The prospect that our most sensitive instruments for studying the universe might be fundamentally influenced by the natural variability of spacetime itself is both humbling and scientifically sobering. It suggests that there might be fundamental limits to how precisely we can measure cosmic phenomena, limits imposed not by our technology but by the intrinsic behaviour of the medium through which all signals must travel. Future space-based gravitational wave detectors will have mirror separations millions of times larger than LIGO's, potentially making them sensitive enough to detect these space-time fluctuations directly. If they succeed, we might finally have direct evidence for the proposed random nature of gravity. If they fail to detect the predicted fluctuations, we'll know that space-time is quieter and more predictable than these theories suggest. Either outcome would be scientifically revolutionary, but the detection of random gravitational fluctuations would confirm that we live in a universe with deeper layers of variability than anyone imagined. Every measurement, every observation, every attempt to understand the cosmos would be subject to fundamental uncertainties that could never be eliminated through improved instruments or techniques. As you consider these possibilities, imagine the implications for humanity's cosmic perspective. We've spent centuries developing increasingly sophisticated tools to study the universe, from Galileo's telescope to space-based observatories that can detect light from the first galaxies. But if space-time itself is fundamentally noisy, then there might be ultimate limits to how clearly we can see into the cosmic distance. Behind these specific predictions lies a broader crisis that has been building in fundamental physics for decades. The dream of a unified theory of everything, a single mathematical framework that could describe all forces and particles, seems increasingly elusive despite enormous intellectual effort and financial investment. String theory, once hailed as the most promising path to unification, requires the existence of multiple extra dimensions that have never been observed and makes predictions that may be impossible to test experimentally. After decades of development by some of the world's most brilliant physicists, it has produced no confirmed predictions about the natural world. Loop quantum gravity, the other major approach to quantum gravity, proposes that space-time itself is made of discrete units at the smallest scales. While mathematically sophisticated, this theory also struggles with testability and has not provided clear experimental predictions that distinguish it from alternative approaches. The persistence of these theories, despite their empirical limitations, reflects a deep faith in the reductionist program that has driven physics for centuries. This program assumes that all phenomena can ultimately be understood in terms of a small number of fundamental laws and particles, ideally unified within a single theoretical framework. But what if this assumption is wrong? What if the universe is not built from a unified foundation, but operates according to fundamentally different principles at different scales? Oppenheim's theory represents a radical departure from unification, suggesting that gravity might remain classical while other forces are quantum, with no deeper unity underlying this division. This possibility is intellectually disturbing because it abandons one of science's most cherished goals. Instead of revealing an elegant underlying unity, the universe might be fundamentally more divided in its operating principles, with rules that cannot be reconciled within a single framework. The search for a theory of everything might be not just difficult, but conceptually misplaced. Consider how this might change our relationship with scientific knowledge itself. For centuries, we've assumed that patient investigation would eventually reveal the universe's deepest secrets, that every mystery would eventually yield to human curiosity and intelligence. But if the universe is fundamentally diverse in its behaviours, operating according to incompatible principles, then complete understanding might be impossible in principle. This doesn't diminish the value of scientific investigation, but it does suggest that we might need to accept permanent mysteries and fundamental limitations on knowledge. The universe might be stranger and more intricately structured than our minds, evolved to navigate a middle-scale world can fully comprehend. As we explore these ideas further, we encounter implications that extend far beyond laboratory measurements or theoretical calculations. If space-time fluctuations play a significant role in cosmic evolution, then the history of the universe itself contains crucial random elements that make it impossible to fully explain why reality looks the way it does. The formation of the first stars, the development of galactic structures, and the emergence of conditions suitable for life might all depend partly on chance events that occurred in the chaotic quantum foam of early space-time. This introduces an element of cosmic contingency into the development of complexity and consciousness. Consider the delicate balance of forces and constants that make life possible in our universe. The strength of gravity, the mass of electrons, the rate of cosmic expansion, all of these seem precisely tuned to allow the formation of atoms, stars, planets, and ultimately living systems. This apparent fine-tuning has inspired both scientific theories and philosophical speculation about why the universe seems so hospitable to complexity. But if space-time fluctuations influence cosmic evolution, then this apparent fine-tuning might be partly the result of random processes rather than deep physical principles. The universe might not be designed for life so much as simply capable of supporting it due to a mix of chance and natural processes, with random space-time fluctuations playing dice with the fundamental constants during cosmic inflation. This possibility transforms questions about cosmic purpose and meaning. Instead of seeking deep reasons why the universe is the way it is, we might need to accept that crucial aspects of reality are fundamentally contingent, dependent on chance events that could have unfolded differently without violating any physical laws. The implications extend to our understanding of consciousness itself. If the conditions that allowed complex information processing systems to emerge were influenced by random space-time fluctuations, then awareness and intelligence might be products of cosmic contingency rather than inevitable outcomes of physical law. This doesn't make consciousness less remarkable or meaningful, but it does situate human awareness within a broader context of cosmic chance and contingency. We are not just products of biological evolution, but participants in a universe-wide process that includes elements of unpredictability at its deepest levels. As you reflect on these ideas, notice how they might influence your sense of place in the cosmos. The emergence of your particular pattern of consciousness, with its unique memories and perspectives, becomes part of a vast cosmic story that includes both law-like regularities and fundamental randomness. Take a breath and imagine what this could mean for how you understand your own existence. You are not just a temporary arrangement of atoms following deterministic laws, but a manifestation of information patterns that emerged from the interplay between quantum mechanics and the proposed variability of space-time fluctuations across billions of years of cosmic evolution. The universe that produced you is neither purely mechanical nor completely random, but something stranger and more subtle. A reality where deterministic quantum evolution meets dynamic space-time behavior, creating conditions where consciousness can emerge from the marriage of order and chaos. The strange mathematics of quantum mechanics suggests something that sounds almost mystical. Every possible outcome of every quantum event may exist simultaneously until the moment of measurement. Some interpretations propose that consciousness itself might play a role in selecting which version of reality we experience, though this remains highly speculative and lacks scientific consensus. Yet when we examine this idea more closely, we find something equally profound but far more grounded: the recognition that our awareness shapes how we interpret and respond to the probabilistic nature of existence itself. Consider the quantum phenomenon of superposition, where particles exist in multiple states simultaneously until observed. While there's no scientific evidence that human consciousness directly collapses quantum wave functions, there's something deeply resonant about the parallel between quantum indeterminacy and the way our own awareness seems to crystallize possibilities into experiences. You wake up each morning to a world that seems solid and predictable, yet quantum mechanics tells us that at the deepest level, reality operates according to probabilities rather than certainties. Every atom in your body, every photon of light illuminating your surroundings, every electrical impulse in your brain involves quantum processes that are fundamentally probabilistic. This isn't just abstract physics, it's the hidden foundation of your moment-to-moment experience. The randomness we've been exploring in gravity finds an unexpected mirror in the quantum realm of consciousness itself. While we cannot scientifically claim that thoughts create reality, we can observe how the probabilistic nature of quantum mechanics echoes something profound about the relationship between awareness and possibility. In quantum mechanics, the observer effect describes how the act of measurement appears to influence the behavior of quantum systems. While this doesn't mean that consciousness has magical powers over matter, it does point to something subtle and important about the role of attention in shaping experience. As you move through your day, notice how the quality of your attention affects what you perceive. When you're anxious, you tend to notice potential threats and problems. When you're curious, details and possibilities that were previously invisible become apparent. When you're calm, patterns and connections emerge that anxiety obscures. This isn't because your thoughts are directly manipulating quantum fields. Such claims lack scientific support. Rather, it's because consciousness operates as a kind of selective filter, determining which aspects of an infinitely complex reality receive attention and processing. The quantum world's probabilistic nature offers a metaphor for understanding how awareness navigates the vast space of possible experiences. Imagine your consciousness as existing in a state similar to quantum superposition, simultaneously containing multiple potential responses to any situation. The moment you become aware of your emotional state, focus your attention, or make a conscious choice, you're selecting one pathway from among many possibilities. This selection doesn't violate physics, but it does demonstrate how awareness participates in determining which version of your potential experience becomes actual. Take a moment to observe your own awareness right now. Notice how simply paying attention to your breathing changes the quality of your experience. You're not altering quantum fields through intention, but you are demonstrating how consciousness serves as an interface between the probabilistic nature of reality and the specificity of lived experience. Perhaps no concept in quantum mechanics has captured the imagination more than entanglement, the phenomenon where particles become correlated in ways that seem to transcend space and time. When two particles become entangled, measuring one instantly affects the other, regardless of the distance between them. Einstein called this spooky action at a distance, and decades of experiments have confirmed its reality. While there's no scientific evidence that human consciousness can become quantum entangled in the same way as particles, the metaphor offers a powerful framework for understanding the subtle ways that awareness connects us to the larger patterns of existence. Some interpretations suggest, though this remains unproven, that consciousness itself might exhibit analogous, not literal, non-local properties similar to quantum entanglement. Consider your own experience of connection and synchronicity. Have you ever thought of someone moments before they contacted you? Have you ever entered a room and immediately sensed the emotional atmosphere, even without any obvious cues? Have you ever felt drawn to make a choice that later proved remarkably well-timed? These experiences might not involve literal quantum entanglement, but they point to something real about how consciousness seems to participate in larger patterns of correlation and connection. The quantum world suggests that separateness might be more apparent than real, that individual particles are embedded in webs of relationship that transcend classical notions of space and time. From this perspective, your individual consciousness doesn't exist in isolation, but as part of a broader pattern of relational awareness, which includes other minds, living systems, and the physical world. This is a speculative idea, not a proven scientific fact, but it offers a framework for understanding experiences of connection that purely materialistic worldviews struggle to explain. As you contemplate these possibilities, notice how the boundaries between self and world begin to feel more permeable. You're not separate from the quantum processes that generate the atoms of your body, or the photons that carry these words to your awareness. You're embedded in the same probabilistic reality that we've been exploring, participant in the same dance of randomness and order that shapes everything from space-time fluctuations to the emergence of conscious experience itself. One of the most unsettling aspects of quantum mechanics is how it challenges our fundamental assumptions about knowledge and certainty. The Heisenberg uncertainty principle tells us that we cannot simultaneously know both the position and momentum of a particle with perfect precision. This isn't just a limitation of our measuring instruments. It appears to be a fundamental feature of reality itself. This quantum uncertainty finds a parallel in the randomness of gravity that we've been exploring. Just as space-time fluctuations might make precise gravitational measurements impossible in principle, quantum mechanics suggests that perfect knowledge of any system is fundamentally unattainable. Reality seems designed to preserve an element of mystery and unpredictability at its deepest levels. Consider how this applies to your own self-knowledge. Despite having privileged access to your own thoughts and feelings, there remain aspects of your consciousness that seem fundamentally mysterious. The origin of thoughts, the nature of awareness itself, the relationship between brain states and subjective experience, all of these remain partially hidden, even from introspection. This isn't a failure of self-awareness, but perhaps a reflection of the quantum nature of the processes that generate consciousness. If awareness emerges from quantum processes in the brain, and this remains an open scientific question, then the uncertainty principle could, metaphorically speaking, apply to consciousness itself. Perfect self-knowledge might be impossible not because we're not paying attention carefully enough, but because awareness participates in the same fundamental indeterminacy that characterizes all quantum systems. This realization can be either disturbing or liberating, depending on how you approach it. If you've been seeking complete control over your thoughts and emotions, quantum uncertainty suggests this might be an impossible goal. But if you're willing to embrace uncertainty as a fundamental feature of existence, it opens space for spontaneity, creativity, and surprise in your relationship with yourself and the world. The random fluctuations in space-time that might make gravitational measurements unpredictable find their psychological parallel in the unpredictable emergence of insights, emotions, and creative inspirations. You cannot force these experiences any more than you can eliminate quantum uncertainty through improved measurement techniques. But you can learn to work with uncertainty as a creative force rather than fighting against it as an obstacle. Quantum field theory, the most fundamental description of reality that physics currently offers, describes particles not as discrete objects, but as excitations in underlying fields that permeate all of space. the electron field, the photon field, the various quark fields. These invisible structures form the foundation from which all material reality emerges. This perspective offers a profound metaphor for understanding consciousness and its relationship to the broader patterns of existence. Some interpretations suggest, though this remains highly speculative, that consciousness itself might be understood as a field phenomenon, a kind of awareness field that manifests as individual minds in much the same way that quantum fields manifest as particles. From this field perspective, your individual consciousness wouldn't be separate from other minds, but would represent a local concentration or excitation within a larger field of awareness. Just as particles in quantum mechanics are temporary patterns in underlying fields, individual minds might be temporary patterns in an underlying consciousness field. This is a speculative idea with no current scientific consensus, but it offers a framework for understanding experiences that suggest consciousness extends beyond the boundaries of individual brains. Collective emotions at gatherings, the apparent transmission of moods between people, the sense of connection with nature or the cosmos, all of these might reflect field-like or emergent properties of awareness itself. If consciousness does have field-like properties, then the random fluctuations in space-time that we've been exploring might influence mental states in subtle but measurable ways. Changes in the gravitational field, fluctuations in electromagnetic fields, even variations in cosmic ray intensity might correlate with shifts in collective mood, creativity, or spiritual experience. Take a moment to sense into the possibility that your awareness extends beyond the boundaries of your physical body. This isn't necessarily a mystical claim, but a recognition that consciousness, like all quantum phenomena, might not respect the classical boundaries that our everyday experience suggests. The metaphorical field that generates your thoughts might overlap and interact with the fields that generate other minds, creating possibilities for connection and influence that purely individualistic worldviews cannot explain. In quantum mechanics, the act of measurement plays a crucial role in determining which of many possible outcomes becomes real. The measurement problem, how and why quantum superpositions collapse into definite states, remains one of the deepest mysteries in physics. Some interpretations propose that consciousness itself serves as the measuring device that collapses quantum possibilities into classical realities, though this idea lacks scientific consensus and remains highly controversial. But even if consciousness doesn't directly collapse quantum wave functions, there's something profound about how awareness serves as a kind of measuring device in your own experience. Every moment of attention, every conscious choice, every shift in awareness represents a kind of measurement that selects one possibility from among many potential experiences. Consider your current state of mind. Right now, as you listen to these words, you're experiencing one particular configuration of thoughts, emotions, and sensations from among countless possibilities. Your attention is focused in a specific way. Your emotional tone has a particular quality. Your level of alertness exists within a certain range. All of these represent selections from vast spaces of possibility. The act of paying attention to your internal state changes that state in measurable ways. Observing your breath affects your breathing patterns. Noticing tension in your body often leads to relaxation. Becoming aware of an emotion transforms your relationship to that emotion. This isn't because observation has magical powers, but because consciousness is an active, participatory process rather than a passive recording device. From this perspective, every moment of awareness involves a kind of psychological or experiential measurement, a selection of one actuality from among multiple potentialities. You're not just observing reality, you're participating in its ongoing creation through the quality and direction of your attention. This participatory aspect of consciousness finds its parallel in the quantum measurement problem. Just as the collapse of quantum superpositions requires some kind of interaction or measurement, the crystallization of your potential experiences into actual experiences requires the active engagement of awareness. You're not separate from the reality you observe, but intimately involved in its moment-to-moment manifestation. One of the most important concepts in quantum mechanics is decoherence, the process by which quantum superpositions lose their coherent wave-like properties and become classical particle-like realities. This typically happens when quantum systems interact with their environment, causing the delicate quantum correlations to break down and disappear. The random fluctuations in space-time that we've been exploring represent one possible mechanism for decoherence. If gravity itself is subject to chaotic variations, then these fluctuations could cause quantum superpositions to collapse more rapidly than they would in perfectly smooth space-time. The universe's built-in randomness might serve as a cosmic decoherence mechanism. This concept offers a powerful metaphor for understanding the relationship between individual consciousness and the larger field of awareness. Just as quantum systems lose their coherent properties when they interact strongly with their environment, individual minds might lose their sense of connection to the larger patterns of consciousness when they become too entangled with local concerns and distractions. Consider your own experience of coherence and decoherence in daily life. There are moments when your awareness feels clear, unified, and connected to something larger than yourself. These might be experiences of deep meditation, creative flow, communion with nature, or profound connection with another person. In these states, the boundaries between self and world become permeable, and you experience something analogous to quantum coherence. But there are also times when your awareness becomes fragmented, scattered, and disconnected. Stress, anxiety, busyness, and mental clutter can cause your consciousness to lose its coherent properties, becoming entangled with random thoughts and emotions in much the same way that quantum systems become entangled with their environment. The practice of meditation and contemplation might be understood as attempts to maintain or restore coherence in consciousness, to prevent awareness from becoming completely decohered by the constant interaction with mental and environmental noise. This doesn't require any mystical beliefs about consciousness, just the recognition that awareness, like quantum systems, seems to have optimal states of organization and function. As you explore these ideas, notice the current coherence of your own awareness. Are your thoughts scattered and reactive, or do they have a sense of unity and direction? Is your attention fragmented by distractions, or does it feel gathered and present? These qualities might reflect the same principles of coherence and decoherence that govern quantum systems. Every choice you make involves selecting one path from among multiple possibilities, collapsing a superposition of potential futures into a single actuality. While this doesn't mean that consciousness operates according to quantum mechanics in any literal sense, the parallel offers insights into the nature of free will and decision-making. Consider a moment of choice in your own life. Perhaps you're deciding whether to continue listening to this exploration or shift your attention to something else. In the moments before you decide, both possibilities exist simultaneously in your awareness. You can imagine the consequences of each choice, feel into the different futures they might create. Sense which option resonates more strongly with your current intentions. The act of choosing represents a kind of collapse, a transition from multiple potentialities to a single actuality. Unlike quantum measurement, this collapse is mediated by factors like values, preferences, reasoning, and intuition, rather than random probability. But the structure of the process, multiple possibilities existing simultaneously until the moment of selection, mirrors the quantum measurement problem. Some interpretations of quantum mechanics, particularly the many worlds theory, suggest that every quantum measurement creates a branching of reality where all possible outcomes occur in parallel universes. If this is true, then every choice you make might similarly create branches in the structure of reality, with different versions of yourself experiencing each possible outcome. This is highly speculative and lacks scientific consensus, but it offers a framework for understanding the weight and significance of conscious choice. Every decision might not just determine your personal future, but contribute to the branching structure of reality itself. Your choices participate in the ongoing creation of the universe, selecting which version of cosmic possibility becomes actual. The randomness in spacetime that we've been exploring adds another layer to this picture. If gravitational fluctuations introduce fundamental uncertainty into the physical processes underlying consciousness, then your choices might involve an interplay between intention and chance that mirrors the relationship between quantum determinism and random collapse. Take a moment to sense the power and responsibility inherent in your capacity for conscious choice. Every decision you make, from the smallest shift in attention to major life changes, represents a kind of cosmic measurement, a selection of one possibility from the infinite space of potential experiences. You're not separate from the quantum processes that generate reality, but intimately involved in their ongoing unfoldment. One of the most mind-bending ideas in modern physics is the holographic principle, which suggests that all the information in a volume of space might be encoded on its boundary. Just as a hologram stores three-dimensional information on a two-dimensional surface, the entire universe might be a kind of holographic projection from information stored on its cosmic boundary. If true, this means that everything you experience, your thoughts, emotions, the objects around you, even the random fluctuations in space-time, might be projections from information stored elsewhere. Reality would be fundamentally informational rather than material, with consciousness and matter emerging from the same underlying computational process. This holographic perspective offers a radical reframe of the relationship between consciousness and reality. Instead of thinking of awareness as something that emerges from complex arrangements of matter, we might consider the possibility that both consciousness and matter are different aspects of the same informational process. This is highly speculative and remains unproven, but it aligns with certain interpretations of quantum mechanics that emphasize the fundamental role of information in physical processes. From this view, your individual consciousness wouldn't be produced by your brain, but would be more like a local access point to the holographic information structure that generates all of reality. Your thoughts and experiences would be real, but they would be aspects of a larger informational process rather than private events occurring inside your skull. The random fluctuations in space-time that might make gravitational measurements unpredictable could represent conceptual or computational noise in the holographic process that generates reality. Just as digital systems are subject to random errors and glitches, the cosmic computer that projects the hologram of existence might introduce elements of fundamental variability that prevent perfect predictability. This perspective doesn't diminish the reality or importance of your subjective experience, but it does suggest that consciousness might be far more fundamental than materialistic worldviews assume. Instead of being a rare accident that occurred on one planet around one star, awareness might be woven into the basic structure of reality itself. As you contemplate these possibilities, notice how they might change your relationship to your own thoughts and experiences. If consciousness is fundamentally informational rather than biological, then your awareness participates in the same computational process that generates stars, galaxies, and the quantum fluctuations we've been exploring. Throughout our exploration, we've encountered the recurring theme that the observer and the observed are not separate but intimately connected. In quantum mechanics, measurement changes what is measured. In consciousness, attention transforms what is attended to. In the random spacetime fluctuations that might make gravity unpredictable, even the act of trying to measure these fluctuations might influence their behavior. This dissolution of the boundary between observer and observed represents one of the most profound shifts in understanding that modern physics offers. The classical worldview assumed that reality exists independently of observation, that consciousness is separate from the world it perceives. But quantum mechanics suggests a more participatory universe where awareness and reality co-evolve through their ongoing interaction. Consider your own experience right now. As you listen to these ideas, you're not passively receiving information, but actively constructing meaning. Your understanding emerges from the interaction between the concepts being presented and your own knowledge, experience, and current state of awareness. The reality you're experiencing is neither purely objective nor purely subjective, but something that emerges from the meeting of consciousness and world. This participatory aspect of experience extends far beyond intellectual understanding to encompass every aspect of your relationship with reality. The quality of your attention affects what you perceive. Your emotional state influences how you interpret events. Your beliefs and expectations shape how you respond to situations. You're not separate from the reality you experience, but intimately involved in its ongoing creation. The random fluctuations in space-time that we've been exploring might represent the universe's way of ensuring that this participatory process remains creative and unpredictable. If reality were completely deterministic, consciousness would have no genuine role to play in its unfoldment. But if fundamental randomness is built into the structure of existence, then awareness becomes a creative force that helps determine which possibilities become actual. This doesn't mean that consciousness has unlimited power over reality. Such claims lack scientific support. But it does suggest that awareness is not separate from the physical processes that generate the world, but intimately woven into their operation. You're not just in the universe is in you, expressing itself through your capacity for conscious experience. As our exploration draws toward its close, we find ourselves contemplating a universe far stranger and more wonderful than the mechanical clockwork that classical physics once imagined. Instead of predictable determinism, we discover elements of unpredictability. Instead of separate objects interacting across empty space, we find fields of possibility that generate the appearance of distinct particles and minds. Instead of passive observation of an independent reality, we encounter participatory awareness, co-creating the world it perceives. The random fluctuations in space-time that might make gravity unpredictable represent just one aspect of a cosmos that seems rich with complexity and surprise at its deepest levels. Whether these fluctuations exist as Oppenheim's theory predicts, or whether gravity ultimately proves to be quantum after all, the search for understanding reveals a reality far more subtle and interconnected than our everyday experience suggests. You are not separate from this cosmic dance, but intimately involved in its ongoing choreography. Every breath you take, every thought you think, every moment of awareness represents a participation in the same processes that generate galaxies, collapse quantum superpositions, and perhaps introduce variability into the fabric of space-time itself. The boundaries between self and cosmos, between observer and observed, between consciousness and reality, prove to be far more permeable than classical worldviews assumed. You exist not as an isolated individual in a foreign universe, but as a temporary pattern in the same fields that generate all of existence. Your awareness is not separate from the quantum processes that underlie physical reality, but can be seen as one expression of the universe's unfolding complexity. Take a moment to rest in this understanding. Feel yourself not as a small separate self struggling to understand a vast incomprehensible cosmos, but as a local concentration of the same awareness that permeates all of existence. It can feel as though you are the universe becoming conscious of itself, participating in its own ongoing creation through the quality and direction of your attention. The randomness we've explored, whether in gravitational fluctuations or quantum measurements, preserves space for genuine creativity and surprise in this cosmic process. You're not trapped in a deterministic mechanism, but invited to participate in an ongoing improvisation where consciousness and cosmos dance together in patterns that can never be fully predicted or controlled. This is both humbling and empowering. Humbling because it reveals how much remains mysterious about the nature of existence. Empowering because it suggests that your awareness plays a meaningful interpretive role in how you experience reality. Your perspective matters, contributing to your unfolding understanding of the universe. As you continue your own journey through this mysterious existence, remember that you carry within yourself the same capacity for wonder that drives scientific discovery, the same awareness that contemplates quantum mysteries, the same creativity that generates the endless diversity of cosmic forms. You are both observer and observed, measurer and measured, participant in the ongoing dance of consciousness and cosmos. If you've been drawn into this exploration of the deepest mysteries, you might find yourself equally fascinated by how this participatory relationship between awareness and reality plays out in the social realm. Our next journey examines how individual consciousness shapes collective reality while being simultaneously shaped by it, in ways that mirror the quantum entanglement we've explored, but manifest in the realm of human relationship and cultural evolution. You're creating everyone's reality, and they're rewriting yours. 2 awaits your attention whenever you feel ready to explore how the cosmic principles we've discovered express themselves in the intimate spaces of human connection and meaning-making. Until then, rest well in the mystery that surrounds and includes you, knowing that every moment of awareness is both a gift to yourself and a contribution to the ongoing unfolding of understanding. The most precise measurement of mass ever attempted sits in a vault in France. Scientists routinely weigh a kilogram standard with instruments so sensitive they can detect changes smaller than the width of an atom. But according to revolutionary new theories, if they measured precisely enough, they would discover something that challenges our deepest assumptions about reality. The weight fluctuates randomly, not because of measurement error, but because space-time itself writhes with chaotic energy that makes even the most basic properties of matter fundamentally uncertain. This isn't a limitation of our instruments. It's a theoretical possibility suggested by certain models of the universe itself. What we're exploring today represents one of the most profound shifts in physics since Einstein showed us that space and time are woven together. The implications reach far beyond academic laboratories into the very foundations of what we think we know about existence. If space-time operates according to random or variable principles rather than purely quantum mechanics, it means the universe might include forms of unpredictability that would have challenged even the most radical physicists of the past century. As you settle into this exploration, whether you're listening during a quiet evening or letting these ideas accompany you toward rest, prepare to encounter concepts that will gently but persistently challenge your assumptions about the nature of reality itself. The evidence we'll examine suggests that the cosmos might be far stranger, more complex, and more mysterious than we've dared to imagine. Deep within the equations that describe black holes lies a prediction so disturbing that many physicists refuse to accept it. Information, the fundamental currency of reality, might not be conserved after all. Every thought you've ever had, every memory you've formed, every pattern of awareness that makes you uniquely you exists as information encoded in the quantum states of your brain. In a universe governed by quantum mechanics, this information would be eternal, perhaps scattered beyond recognition, but never truly destroyed. But Oppenheim's theory suggests something different. It proposes that black holes don't just hide information behind their event horizons, they consume it entirely, potentially altering or eliminating informational patterns in ways that challenge quantum mechanics' most sacred principle. The implications ripple outward, like stones dropped into still water, touching questions about memory, consciousness, and whether anything in the universe can truly be said to last forever. Consider what this means for the patterns of information that constitute your own awareness. As you process these words, connecting them with existing memories and forming new understandings, you're creating intricate arrangements of data that represent your unique perspective on existence. In a quantum universe, these patterns would persist in some form even after the biological processes that sustain them cease. But if black holes can disrupt or remove information, then consciousness itself becomes fragile in ways that purely materialistic worldviews cannot capture. This fragility extends beyond individual minds to encompass the entire record of cosmic history. Every star that has ever formed, every planet that has ever supported life, every moment of awareness that has ever flickered into existence leaves an informational signature in the quantum structure of reality. If this information can be lost or fundamentally transformed, then the universe becomes a place where even the deepest truths can fade from trace. The mathematics behind this possibility emerge from attempts to resolve the black hole information paradox, one of theoretical physics' most persistent puzzles. When matter falls into a black hole, its information seems to disappear when the black hole eventually evaporates through Hawking radiation. Quantum mechanics insists this is impossible, leading to elaborate theories about information storage on black hole surfaces and holographic principles that encode three-dimensional reality on two-dimensional boundaries. Oppenheim's approach cuts through this complexity with elegant brutality. Under his proposal, information can be destroyed. Black holes are sometimes described metaphorically as cosmic deletion machines that remove patterns from existence with perfect efficiency. This resolves the paradox, but at the cost of abandoning one of physics' most fundamental assumptions about the permanent nature of information. As you contemplate these ideas, notice how they might shift your relationship with your own thoughts and experiences. If information can be irreversibly altered, then the patterns of awareness that constitute your identity have a fundamental fragility that goes beyond biological mortality. They exist in a universe where permanence itself might be an illusion, where even the deepest truths can be lost to processes beyond current understanding. This doesn't diminish the reality or importance of consciousness, but it does suggest that awareness exists within a larger context of cosmic impermanence that makes every moment of clarity and understanding precious in ways that purely materialistic or purely spiritual worldviews struggle to capture. In the depths of Antarctic ice, buried beneath miles of frozen water, lies one of humanity's most ambitious attempts to eavesdrop on the universe's deepest conversations. The Ice Cube Neutrino Observatory captures particles that have travelled billions of light-years through space, carrying messages from the most violent and distant corners of the cosmos. These ghostly messengers interact with matter so rarely that they can pass through entire planets without leaving a trace, making them perfect couriers for testing our most fundamental theories about the nature of space-time itself. What makes neutrinos particularly valuable for probing quantum gravity is their almost complete isolation from the forces that dominate everyday matter. They experience only the weak nuclear force and gravity, travelling across cosmic distances without the electromagnetic interactions that scatter photons, or the strong force interactions that bind quarks into protons and neutrons. This isolation allows them to preserve quantum coherence over macroscopic distances, turning them into natural interferometers for detecting spacetime's finest structure. The results of studying over 300,000 of these cosmic travellers have been both illuminating and puzzling. If spacetime were truly quantum at the deepest level, the passage of neutrinos through quantum fluctuations in gravity should leave subtle but detectable signatures in their properties. The oscillation between different types of neutrinos, a purely quantum phenomenon, should be disturbed by quantum gravitational effects in measurable ways. But no such disturbances have been found, despite experimental sensitivity that exceeds previous limits by over 1 million times. This absence of evidence doesn't prove that spacetime isn't quantum, but it does suggest that if quantum gravitational effects exist, they are far smaller than many theories predict. The neutrinos arrive at Earth carrying a message written in the language of their unperturbed quantum states. The vast emptiness through which they travelled might be quieter and more classical than we assumed. This finding lends indirect support to theories like Oppenheim's that propose gravity might remain classical, while other forces follow quantum rules. If spacetime doesn't exhibit quantum behaviour on the scales these sensitive experiments can probe, perhaps we need to seriously consider alternatives to the century-long quest to quantize gravity. The cosmos might be telling us through these ancient messengers that unification isn't the goal of physics, after all. The implications extend far beyond academic debates about quantum gravity to touch on our most basic assumptions about the nature of scientific knowledge itself. For decades, physicists have assumed that patient investigation would eventually reveal a unified theory of everything, a single mathematical framework that could describe all forces and particles. But what if the universe isn't built from unified foundations? What if reality operates according to fundamentally different principles at different scales, with no deeper unity underlying this division? Take a moment to consider how this possibility might change your understanding of existence itself. Instead of revealing an elegant underlying unity, the universe might be fundamentally fragmented, operating according to incompatible rules that can never be reconciled. The search for a theory of everything might be not just difficult, but potentially misplaced, a category error based on human assumptions about how reality should be organized, rather than observations about how it actually behaves. This doesn't diminish the value of scientific investigation, but it does suggest that we might need to accept permanent mysteries and fundamental limitations on knowledge. The universe might be stranger and more compartmentalized than our minds, evolved to navigate a middle-scale world can fully comprehend. Every second, gravitational waves from colliding black holes and neutron stars sweep through Earth at the speed of light, stretching and compressing space itself by amounts smaller than 1,000th the width of a proton. The Laser Interferometer, Gravitational Wave Observatory, detects these cosmic ripples by measuring incredibly tiny changes in the length of laser beams, traveling between mirrors separated by several kilometers. It's one of the most precise measurements ever attempted, capable of detecting disturbances that would be invisible to any conceivable mechanical instrument. But if space-time is subject to random fluctuations, as theories of classical gravity with built-in randomness suggest, then LIGO's measurements might be constantly contaminated by noise that has nothing to do with distant cosmic collisions. The detectors might be perpetually bombarded by chaotic variations in the gravitational field that could mask genuine signals or create false detections. What we interpret as messages from the cosmic deep might be partially composed of the universe's own underlying variability. Recent theoretical work suggests that dark matter, if it consists of ultralight particles, could create its own fluctuations in space-time that would appear as background noise in gravitational wave detectors. These disturbances would be like waves in an invisible ocean, constantly jostling the mirrors and introducing uncertainty into measurements that we thought were limited only by technical precision. The analogy to ocean waves is particularly apt. Just as the surface of the sea exhibits unpredictable fluctuations that extend far beyond what any single wave might suggest, the dark matter halo surrounding our galaxy might undergo random density changes that jostle entire gravitational wave observatories. The prospect that our most sensitive instruments for studying the universe might be fundamentally compromised by the inherent variability of space-time itself is both humbling and scientifically exciting. It suggests that there might be ultimate limits to how precisely we can measure cosmic phenomena, limits imposed not by our technology, but by the possible intrinsic noise of the medium through which all signals must travel. Future space-based gravitational wave detectors will have mirror separations millions of times larger than LIGO's, potentially making them sensitive enough to detect these space-time fluctuations directly. If they succeed in measuring the predicted random variations, we would have direct evidence that the universe is far more dynamically complex than anyone imagined. Every measurement, every observation, every attempt to understand the cosmos would be subject to fundamental uncertainties that could never be eliminated through improved instruments or techniques. But if these space-based detectors fail to find the predicted fluctuations, we would learn something equally profound: that space-time is quieter and more predictable than these theories suggest. Either outcome would revolutionize our understanding of gravity, but the detection of random gravitational noise would confirm that we live in a universe where precision itself has natural limits written into the fabric of reality. As you contemplate these possibilities, imagine the implications for humanity's cosmic perspective. We've spent centuries developing increasingly sophisticated tools to study the universe, from Galileo's telescope to space-based observatories that can detect light from the first galaxies. But if space-time itself is fundamentally noisy, then there might be ultimate limits to how clearly we can see into the cosmic distance, barriers imposed not by distance or time, but by the baseline variability of empty space itself. This realization invites a different kind of humility in our relationship with cosmic knowledge. Instead of assuming that patient investigation will eventually reveal all secrets, we might need to accept that some aspects of the universe will remain forever mysterious, not because we lack the tools to study them, but because reality itself preserves an element of irreducible uncertainty that cannot be eliminated through any technological advance. In a secure facility in France, scientists maintain the international prototype kilogram, a cylinder of platinum-iridium alloy that once served as the definition of mass itself. This unassuming object, roughly the size of a golf ball, represents humanity's attempt to create absolute standards in a universe that might be fundamentally unstable. According to Oppenheim's theory, if measurements of this standard mass were precise enough, they would reveal something deeply unsettling. The weight could fluctuate slightly over time, not due to any external influence, but because space-time itself introduces uncertainty into the most basic properties of matter. The proposed experimental test is elegant in its simplicity and revolutionary in its implications. Measure the mass of an object with extraordinary precision over extended periods and look for variations that exceed what classical physics would allow. If the predicted fluctuations are observed, it would confirm that space-time operates according to variable or stochastic principles. If the fluctuations are smaller than the theory requires, the theory can be ruled out. Either outcome would be scientifically significant, but a positive result would transform our understanding of reality itself. Consider what this means for your most basic assumptions about the physical world. We expect that identical objects should have identical weights, that measurements should be reproducible, and that the physical properties of matter should remain constant over time. But if space-time itself is subject to random fluctuations, then even these fundamental expectations might be subject to subtle variations. The solid objects that surround you, the ground beneath your feet, even your own body might be subject to tiny but real variations that make their properties fundamentally uncertain. This uncertainty isn't a limitation of our measurement techniques, but a basic feature of reality itself. The randomness would be woven into the fabric of existence at the deepest level, making certain types of knowledge impossible in principle, rather than just practically difficult to obtain. Precision instruments that rely on exact masses or distances might be fundamentally limited, not by technical imperfections, but by the intrinsic variability of space-time itself. The implications extend far beyond scientific measurements to touch on practical questions about technology and engineering. Navigation systems that depend on precise timing might be subject to random errors that cannot be eliminated through improved design. Atomic clocks, the foundation of GPS and other critical technologies, might exhibit variations caused not by instrumental drift, but by fluctuations in the gravitational field itself. Manufacturing processes that require exact specifications might need to account for fundamental uncertainties that make perfect reproducibility impossible. Even architectural and engineering calculations might need to incorporate statistical variations that reflect the potentially fluctuating nature of space-time, rather than just the imperfections of materials and construction techniques. As you reflect on these possibilities, notice how they might change your relationship with the physical world around you. The experience of stability and predictability that characterizes everyday life might be an emergent property that obscures deeper layers of uncertainty and randomness. The chair you're sitting in, the device you're using to listen to these words, the air you're breathing, all exist within a context of cosmic uncertainty that makes their apparent solidity a kind of statistical miracle. This doesn't mean that the physical world is unreliable in practical terms, but it does suggest that the foundations of material reality might be more mysterious and less rigid than common sense assumes. The universe might be fundamentally probabilistic, not just at the quantum level, but at every scale, with randomness serving as a creative force that prevents existence from becoming completely predictable and mechanical. Dark matter, the invisible substance that comprises 85% of all matter in the universe, has remained one of cosmology's greatest mysteries despite decades of increasingly sophisticated searches. Massive underground detectors, space-based telescopes, and particle accelerators have all failed to directly observe the exotic particles that most theories propose to explain dark matter's gravitational effects. But what if we've been looking for the wrong thing entirely? Some theoretical approaches suggest that what we interpret as evidence for dark matter might actually be the result of random fluctuations in spacetime itself. The anomalous behaviour of stars in the outer regions of galaxies, which led astronomers to propose dark matter in the first place, could potentially be explained by the cumulative effects of gravitational noise rather than invisible particles. The energy that keeps stars moving at unexpected speeds might come from random variations in the fabric of space and time. These effects would be strongest where gravity is weakest, precisely the regions where dark matter's influence is most apparent. This creates an intriguing possibility. One of the universe's greatest mysteries might be solved not by discovering exotic particles, but by recognizing the fundamentally variable nature of space-time itself. The search for dark matter, involving billions of dollars in research funding and the construction of massive underground laboratories, might have been misdirected if such models prove accurate. If space-time fluctuations can account for galactic dynamics, then the universe becomes simpler in some ways but more chaotic in others. We wouldn't need to populate the cosmos with invisible particles that interact only gravitationally, but we would need to accept that the large-scale structure of the universe is governed by random processes that make cosmic evolution fundamentally unpredictable. This possibility transforms our understanding of cosmic development from a story of gravitational assembly guided by predictable physical laws into something more like a vast probabilistic process. The formation of galaxies, the collision of galaxy clusters, and the emergence of the cosmic web itself might all contain crucial random elements that could have unfolded differently without violating any physical principles. Imagine galaxies as islands in a dynamic sea of space-time fluctuations, their motion influenced not only by the gravitational pull of visible matter, but also by invisible waves of random energy that surge and ebb according to no discernible pattern. The stately rotation of spiral galaxies, the dynamics of galaxy clusters, and the flow of matter through cosmic voids would all contain elements of fundamental unpredictability. The implications for our understanding of cosmic purpose and meaning are profound. If space-time fluctuations played a significant role in shaping the universe, then the conditions that allowed stars, planets, and ultimately life to emerge might depend partly on chance events rather than inevitable consequences of physical law. The apparent fine-tuning of cosmological constants that makes complexity possible could be partly influenced by early universe variability rather than deep design principles. This doesn't make the emergence of consciousness less remarkable, but it does situate awareness within a broader context of cosmic contingency. We might be products not just of biological evolution, but participants in a universe-wide process that includes elements of unpredictability at its deepest levels. The particular configuration of matter and energy that makes your consciousness possible could be partly the result of space-time fluctuations that occurred during the universe's earliest moments. Take a breath and consider what this might mean for your understanding of your own existence. You're not just a temporary arrangement of atoms following deterministic laws, but a manifestation of information patterns that emerged from the interplay between order and fundamental variability across billions of years of cosmic evolution. Your awareness represents a kind of cosmic achievement, the universe developing the capacity to know itself through processes that include both law-like regularities and natural randomness. For nearly a century, theoretical physics has been driven by the dream of unification, the belief that all forces and particles could eventually be described by a single, elegant, mathematical framework. This quest has produced some of science's most ambitious theories: string theory with its multiple extra dimensions, loop quantum gravity with its discrete spacetime, and various attempts to merge quantum mechanics with general relativity into a theory of quantum gravity. But what if this entire enterprise has been based on a false assumption? What if the universe isn't built from unified foundations, but operates according to fundamentally different principles at different scales? Oppenheim's theory represents a radical departure from the unification paradigm, suggesting that gravity might remain forever classical, while other forces follow quantum rules, with no deeper unity underlying this division. The persistence of unification theories, despite their empirical limitations, reflects a deep faith in the reductionist program that has driven physics for centuries. This program assumes that all phenomena can ultimately be understood in terms of a small number of fundamental laws and particles, ideally unified within a single theoretical framework. The success of this approach in areas like electromagnetism and the standard model of particle physics has reinforced the belief that unification is not just possible, but inevitable. String theory, once hailed as the most promising path toward a theory of everything, requires the existence of multiple extra dimensions that have never been observed, and makes predictions that may be impossible to test experimentally. After decades of development by some of the world's most brilliant physicists, it has produced no confirmed predictions about the natural world that distinguish it from alternative approaches. Loop quantum gravity, the other major candidate for quantum gravity, proposes that space-time itself is made of discrete units at the smallest scales. While mathematically sophisticated, this theory also struggles with experimental testability and has not provided clear predictions that would allow it to be definitively confirmed or ruled out through observation. The failure of these approaches after decades of intensive research raises challenging questions about whether the unification program itself might be fundamentally misguided. Perhaps the universe is not built like a grand mechanical system where all parts fit together according to a master plan. Perhaps reality is more like a patchwork quilt where different regions follow different rules, with no underlying unity to be discovered. This possibility is intellectually disturbing because it abandons one of science's most cherished goals. Instead of revealing an elegant underlying order, the universe might be fundamentally fragmented, operating according to incompatible principles that can never be reconciled within a single theoretical framework. The search for a theory of everything might be not just difficult, but conceptually inappropriate, a category error based on human aesthetic preferences rather than the actual structure of reality. Consider how this might change our relationship with scientific knowledge itself. For centuries, we've assumed that patient investigation would eventually reveal the universe's deepest secrets, that every mystery would eventually yield to human curiosity and intelligence. But if the universe is fundamentally divided against itself, operating according to incompatible principles, then complete understanding might be limited in principle rather than just practically difficult. This doesn't diminish the value of scientific investigation, but it does suggest that we might need to accept permanent mysteries and fundamental limitations on knowledge. The universe might be stranger and more compartmentalized than our minds, evolved to navigate a middle-scale world of moderate temperatures and familiar forces can fully comprehend. If you enjoy drifting through these explorations of fundamental mysteries without interruption, members get every episode 48 hours early, completely ad-free. You can join them whenever you feel ready. One of quantum mechanics' most persistent puzzles is the measurement problem, the question of how and why quantum superpositions collapse into definite states when observed. In standard quantum theory, particles exist in multiple states simultaneously until something measures them. An electron can spin both up and down at the same time, a photon can travel multiple paths simultaneously, and quantum systems can exhibit the strange property of being in several different conditions at once. But the moment we observe these systems, the superposition collapses, and we see only one definite outcome. This process has puzzled physicists for nearly a century because quantum mechanics provides no clear mechanism for why or how this collapse occurs. The theory simply postulates that measurements cause collapse without explaining what constitutes a measurement or why the universe should behave this way. Various interpretations have been proposed to resolve this puzzle. Some suggest that consciousness plays a role in collapse. Others propose that the universe splits into multiple branches where every possible outcome occurs. Still others invoke hidden variables or pilot waves that guide quantum systems toward definite outcomes. But these solutions often raise more questions than they answer, leading to philosophical debates that seem increasingly disconnected from experimental reality. Oppenheim's theory offers a radically different solution that eliminates the measurement problem entirely. Quantum superpositions collapse naturally through their interaction with randomly fluctuating spacetime. There's no need for conscious observers, special measurement devices, or splitting universes. The natural variability of spacetime itself provides the mechanism that transforms quantum possibilities into classical realities. This resolution is both elegant and unsettling. It removes the mystery from quantum measurement by making spacetime the agent of collapse, but it does so by introducing fundamental randomness into the gravitational field itself. The universe doesn't need conscious observers to collapse wave functions because spacetime is constantly shifting with subtle fluctuations that force quantum systems to choose definite states. In this view, the solid classical world we experience emerges from the marriage of quantum possibilities and dynamically fluctuating spacetime. The definite objects with specific properties that characterize everyday experience don't depend on consciousness or mysterious measurement processes. They depend on the underlying variability of the gravitational field that surrounds and permeates everything in the universe. Consider what this means for your immediate environment, the chair you're sitting in, the device you're using to listen to these words, the air you're breathing. All of these exist in definite states, not because they were measured by conscious observers, but because they're constantly interacting with a space-time that fluctuates chaotically at levels too small to detect directly, but large enough to collapse quantum superpositions into classical realities. This perspective transforms our understanding of the relationship between quantum mechanics and everyday experience. Instead of needing to explain how the quantum world gives rise to classical phenomena through mysterious measurement processes, we can understand classical reality as the natural result of quantum systems interacting with subtle, ever-present space-time variability. The mystery isn't how quantum superpositions collapse, but how they manage to persist at all in a universe where space-time itself is constantly disturbing them. The implications extend beyond academic physics to touch on fundamental questions about the nature of existence itself. If space-time fluctuations are responsible for collapsing quantum superpositions, then the solid, predictable world we inhabit emerges from a deeper layer of reality that is fundamentally chaotic and unpredictable. Our experience of stability and determinism becomes a kind of statistical miracle, an emergent property of chaotic processes that we cannot directly perceive. As you reflect on these ideas, notice how they might shift your understanding of the relationship between order and chaos in your own experience. The predictable patterns of daily life, the reliable behavior of physical objects, even the consistency of your own thoughts and memories, all emerge from underlying processes that might be far more random and uncertain than common sense suggests. Perhaps the most philosophically disturbing aspect of theories that allow information to be destroyed concerns the nature of memory, meaning, and the permanent significance of existence. In quantum mechanics, information is conserved with mathematical precision. Every particle interaction, every quantum measurement, every moment of physical process leaves an indelible mark on the structure of reality. Nothing is ever truly lost, only transformed in ways that make it practically inaccessible. This conservation principle extends far beyond abstract physics to encompass questions about consciousness, identity, and the ultimate fate of everything we consider meaningful. Every thought you've ever had, every emotion you've experienced, every moment of awareness that has flickered through your mind exists as information encoded in the quantum states of your brain. In a universe where information is conserved, these patterns would persist eternally, perhaps scattered beyond recognition, but never truly erased. But if information can be destroyed, as Oppenheim's theory suggests might happen in black holes, then consciousness itself becomes fragile in ways that purely materialistic worldviews cannot capture. The patterns that constitute your identity, your memories, your unique perspective on existence could in principle be disrupted or eliminated if they ever encountered the right kind of cosmic environment. This isn't merely a theoretical concern about distant astronomical objects. Black holes exist throughout the universe, from stellar mass objects formed by collapsing stars to supermassive behemoths at the centers of galaxies. Our own galaxy contains millions of black holes, and the supermassive black hole at the Milky Way's center regularly consumes matter from its surroundings. If these objects can remove information, then the universe contains countless mechanisms for erasing informational patterns associated with consciousness, memory, and meaning. The philosophical implications ripple outward like waves from a stone dropped into still water. If information can be destroyed, what does this say about the ultimate significance of existence? Religious and spiritual traditions often find comfort in the idea that something permanent underlies the temporary nature of physical life, whether this is conceived as an immortal soul, a universal field of awareness, or simply the mathematical structure of information itself. But theories that allow information destruction challenge even these deepest sources of meaning by suggesting that the universe might be capable of genuine loss. Consider what this means for the story of your own life. Every experience that has shaped you, every relationship that has mattered to you, every moment of insight or understanding you've achieved exists as patterns of information. In a universe where information can be destroyed, these patterns have a fundamental vulnerability that extends beyond the biological limits of memory. They exist within a reality where permanence cannot be guaranteed, given sufficient time and the right cosmic circumstances. This perspective doesn't necessarily diminish the value or meaning of conscious experience, but it does situate awareness within a context of cosmic impermanence that makes every moment of clarity precious in ways that neither purely materialistic nor traditionally spiritual worldviews fully capture. If the universe can forget, then remembering becomes an act of defiance against cosmic entropy, a way of preserving meaning in the face of ultimate uncertainty. The destruction of information in black holes would represent something qualitatively different from ordinary forgetting or the gradual decay of physical systems. When a computer hard drive fails or a book crumbles with age, the information they contained isn't destroyed but merely scattered into forms that are no longer accessible. The quantum states that encoded that information are redistributed throughout the environment in ways that preserve the total information content of the universe. But if black holes can genuinely delete information, they would represent cosmic erasers that remove patterns from existence with absolute finality. The information wouldn't be hidden or transformed beyond recognition, it would simply cease to exist in any form. This creates a universe where certain kinds of forgetting are complete, where some patterns can be lost, not just to practical access, but to reality itself. As you contemplate these possibilities during a quiet moment in your day, notice how they might influence your relationship with your own thoughts and memories. The patterns of awareness that constitute your unique perspective on existence become precious not just because they define your individual identity, but because they participate in the universe's capacity to know itself through conscious observation. In a reality where information can be destroyed, every moment of awareness represents a fleeting but meaningful contribution to the universe's ongoing emergence. Throughout our exploration, we've encountered a theme that appears again and again, like a musical motif woven through a complex composition. Uncertainty is not a flaw in the universe's design, but a fundamental feature that enables creativity, prevents complete predictability, and preserves space for genuine novelty. Whether we're examining quantum superpositions, gravitational fluctuations, or the collapse of wave functions through spacetime interactions, we find a cosmos that seems designed to resist complete knowledge and perfect control. This resistance to certainty appears at every scale of existence. At the quantum level, the Heisenberg uncertainty principle tells us that we cannot simultaneously know both the position and momentum of a particle with perfect precision. This isn't a limitation of our measuring instruments, but a fundamental property of reality itself. Nature seems to insist on preserving an element of mystery at its deepest levels. The random fluctuations in space-time that we've been exploring represent another manifestation of this cosmic uncertainty principle. If gravity itself is subject to chaotic variations, then even the most basic measurements of mass and weight become probabilistic rather than deterministic. The universe refuses to be pinned down with absolute precision, maintaining a kind of creative ambiguity that makes perfect prediction impossible. But this uncertainty is not chaotic in the sense of being completely random or meaningless. Instead, it follows statistical patterns that can be described mathematically and predicted probabilistically. It's like a jazz improvisation that follows certain harmonic rules while remaining spontaneous and unpredictable in its specific expressions. The universe improvises within constraints, creating endless variations on fundamental themes. Consider how this principle of creative uncertainty might manifest in your own experience. There are aspects of your consciousness that seem to follow predictable patterns, the habits of thought and behavior that give your personality its characteristic shape. But there are also moments of genuine surprise, insights that emerge from nowhere, creative inspirations that cannot be forced or predicted. These experiences might reflect your participation in the same uncertainty principle that governs quantum mechanics and potentially gravitational fluctuations. The emergence of consciousness itself might depend on this cosmic uncertainty principle. If the universe were completely deterministic, with every outcome perfectly predictable from initial conditions, there might be no space for the kind of creative information processing that characterizes aware systems. But if fundamental randomness is built into reality at multiple levels, then consciousness becomes a way that the universe explores its own possibilities through the experiences of aware beings. This doesn't mean that consciousness violates physical laws or operates according to supernatural principles. Rather, it suggests that awareness might be one of the ways that the universe's built-in uncertainty expresses itself at scales large enough for us to experience directly. Your thoughts, emotions, and creative insights emerge from the same probabilistic processes that generate quantum superpositions and potentially gravitational fluctuations. Take a moment to notice the quality of uncertainty in your current experience. Are there aspects of your mental state that feel genuinely unpredictable? Elements of your awareness that resist your attempts to control or predict them? These qualities might reflect your participation in the cosmic uncertainty principle, your embodiment of the same creative ambiguity that characterizes reality at its deepest levels. As we approach the conclusion of our journey through these mind-bending concepts, we find ourselves contemplating a universe that is far more dynamic, interconnected, and mysterious than the mechanical clockwork that classical physics once imagined. Instead of predictable determinism governing every interaction, we discover layers of uncertainty and randomness that preserve space for creativity and genuine novelty at every scale. The random fluctuations in space-time that might make gravity unpredictable represent just one note in a cosmic symphony that includes quantum superpositions, information processing in consciousness, the collapse of wave functions, and the possible destruction of information in black holes. Each of these phenomena reflects the same underlying theme. Reality is not a fixed, predetermined structure, but an ongoing improvisation that balances order with chaos, predictability with surprise. You are not separate from this cosmic dance, but intimately involved in its ongoing choreography. Every breath you take participates in the same thermodynamic processes that drive stellar evolution. Every thought you think emerges from quantum processes that might be influenced by the same uncertainty principles that govern particle interactions. Every moment of awareness represents a way that the universe comes to know itself through conscious observation. The boundaries between observer and observed, between consciousness and cosmos, between self and universe, prove to be far more permeable than classical worldviews assumed. You exist not as an isolated individual in a foreign reality, but as a temporary pattern in the same fields of possibility that generates galaxies, collapse quantum superpositions, and potentially introduce random fluctuations into the fabric of space-time itself. This perspective invites a profound shift in how you understand your place in the cosmic order. Instead of being a small, insignificant speck in a vast, indifferent universe, you become a local concentration of the same awareness that permeates all of existence. Your consciousness is not separate from the physical processes that generate reality, but represents one of the ways that matter and energy organize themselves into patterns capable of self-reflection and creative response. The randomness we've explored, whether in gravitational fluctuations, quantum measurements, or the collapse of superpositions, preserves space for genuine creativity and surprise in this cosmic process. You're not trapped in a deterministic mechanism, but invited to participate in an ongoing improvisation where consciousness and cosmos dance together in patterns that can never be fully predicted or controlled. This is both humbling and empowering. Humbling because it reveals how much remains mysterious about the nature of existence, how many questions we cannot answer with current knowledge and techniques, but empowering because it suggests that your awareness plays a genuine role in the ongoing creation of reality, not through magical thinking or wishful projection, but through the quality and direction of your attention as it engages with the probabilistic processes that characterize existence at every level. The scientific discoveries we've explored don't diminish the mystery of consciousness, but deepen it by revealing the extraordinary complexity and subtlety of the physical processes from which awareness emerges. Far from reducing mind to mere mechanism, quantum mechanics and theories of gravitational fluctuations suggest that the universe is far stranger and more creative than purely mechanical models can capture. As you continue your own journey through this mysterious existence, remember that you carry within yourself the same capacity for wonder that drives scientific discovery, the same awareness that might collapse quantum superpositions, the same creative potential that generates the endless diversity of cosmic forms. You are both observer and observed, measurer and measured, participant in the eternal dance of consciousness and cosmos. The questions we've explored together, from the randomness of gravity to the potential destruction of information in black holes, remain open. The experiments that could confirm or refute these theories are still being designed and conducted. You're witnessing science at its most adventurous and uncertain, exploring ideas that could revolutionize our understanding of reality itself. But regardless of how these specific theories fare in the face of experimental testing, the deeper themes they represent will likely persist. The universe appears to be far more subtle, interconnected, and creative than our everyday experience suggests. Reality operates according to principles that preserve mystery and uncertainty at its deepest levels, making complete knowledge impossible while keeping the cosmos perpetually capable of surprising us. If you've been drawn into this exploration of how randomness and uncertainty shape the deepest levels of physical reality, you might find yourself equally fascinated by how these same principles play out in the realm of human consciousness and social interaction. Our next journey examines how individual awareness shapes collective reality while being simultaneously influenced by it, in ways that mirror the quantum entanglement we've explored, but manifest in the intimate spaces of relationship, culture, and shared meaning-making. You're creating everyone's reality, and they're rewriting yours. Two awaits your attention whenever you feel ready to explore how the cosmic principles we've discovered express themselves in the social dimensions of existence, where consciousness meets consciousness in the ongoing creation of shared worlds. Until then, rest well in the mystery that surrounds and includes you, knowing that every moment of awareness is both a gift to yourself and a contribution to the ongoing awakening of the cosmos itself. It can feel as though the universe expresses itself through your consciousness, and your dreams participate in the larger dreaming of existence. In that reciprocal relationship between individual awareness and cosmic creativity, we find perhaps the deepest meaning of all, that to be conscious is to feel part of a larger creative process, and to be creative is to participate in the endless becoming of everything that is. As we drift deeper into these contemplations about the random nature of space-time, we encounter a realm where the boundaries between the cosmic and the personal begin to blur in unexpected ways. The same uncertainty principles that might govern gravitational fluctuations could also illuminate something profound about the nature of consciousness itself, not through direct causal mechanisms, but through the elegant parallels that emerge when we examine how awareness navigates probability and possibility. Consider for a moment the experience of dreaming. Each night, as you slip into unconsciousness, your mind constructs elaborate worlds from fragments of memory, emotion, and pure imagination. These dream realities feel completely convincing while you're experiencing them, yet they operate according to logic that would be impossible in waking life. Objects transform without warning, people shift identities mid-conversation, and the laws of physics bend in ways that your dreaming mind accepts without question. There's something deeply resonant between the quantum world's superposition of multiple states and the dream mind's ability to hold contradictory realities simultaneously. In dreams, you can be both yourself and someone else, exist in multiple locations at once, experience events that are simultaneously past and future. This isn't because dreams operate according to quantum mechanics in any literal sense, but because consciousness itself seems to have a natural affinity for the kind of probabilistic non-linear relationships that characterize quantum systems. The random fluctuations in space-time that we've been exploring might offer a metaphor for understanding how creative insights emerge from the unconscious mind. Just as gravitational noise could introduce unpredictable elements into physical measurements, the chaos of neural activity during sleep might generate the unexpected connections and novel combinations that characterize breakthrough thinking and artistic inspiration. Take a breath and reflect on your own experience of creative emergence. Have you ever awakened with a solution to a problem that had seemed intractable the night before? Have you found yourself suddenly understanding something that had previously been confusing, without being able to trace the logical steps that led to the insight? These experiences suggest that consciousness might operate according to principles that parallel the uncertainty and randomness we find in fundamental physics. This doesn't mean that thoughts create reality or that dreams influence quantum fields. Rather, it points to something more subtle, the possibility that awareness and physical reality might both emerge from the same underlying patterns of possibility and actualization. Both consciousness and cosmos might be expressions of a deeper creative principle that balances order with chaos, predictability with surprise, determinism with genuine novelty. The quality of your attention shapes not just what you perceive, but how you perceive it, creating a kind of observational selection effect that parallels, though it doesn't duplicate, the measurement problem in quantum mechanics. When you're anxious, you tend to notice potential threats and problems that were always present in your environment but previously invisible to your focused awareness. When you're curious and open, details and possibilities emerge that anxiety would have filtered out entirely. This selective nature of attention doesn't mean that consciousness determines what exists in the external world, but it does suggest that the interface between awareness and reality is far more active and participatory than purely passive models of observation would suggest. You're not simply recording what's already there like a biological camera, but actively constructing your experienced reality through the choices you make about where to focus, how long to sustain attention, and what interpretive frameworks to apply to incoming information. The random fluctuations in spacetime that might make gravitational measurements fundamentally uncertain find their experiential parallel in the way that consciousness seems to sample from vast spaces of possibility, rather than exhaustively processing all available information. Your brain receives millions of sensory inputs every second, but only a tiny fraction of this data reaches conscious awareness. The selection process that determines which inputs become conscious experiences might operate according to principles that are inherently probabilistic rather than strictly deterministic. This probabilistic sampling creates an interesting parallel with quantum measurement. Just as quantum systems seem to exist in superpositions of multiple states until observation selects one outcome, your potential experiences might exist in a kind of attentional superposition until the focusing of awareness collapses them into actual conscious content. This is a metaphorical relationship, not a literal quantum effect, but it points to deep structural similarities between how consciousness and quantum systems navigate possibility spaces. Consider how this might appear in your daily experience. At any given moment, you could focus your attention on the sensation of breathing, the sounds in your environment, the flow of thoughts through your mind, or the emotional tone of your current state. Each of these represents a different collapse of your attentional superposition, a selection of one aspect of reality from among many simultaneously available options. The choice of where to place your attention doesn't create the phenomena you observe, but it does determine which aspects of reality become central to your experience and which remain in the background. This selective attention creates feedback loops that can amplify certain patterns while allowing others to fade, gradually shaping both your internal state and your behavioral responses to the world around you. As you notice the current direction of your own attention, observe how simply becoming aware of your attentional choices changes the quality of your experience. This metacognitive awareness, the capacity to observe your own observing, creates recursive loops that add layers of complexity to the relationship between consciousness and reality that purely mechanical models struggle to capture. Emotions, those subtle currents that colour every moment of conscious experience, might offer another window into understanding how individual awareness participates in larger patterns of organisation and relationship. While there's no scientific evidence that emotional states directly influence quantum fields or physical processes in the external world, emotions do seem to exhibit field-like properties that create correlations and influences across space and time in ways that purely individualistic models of mind cannot fully explain. Consider what happens when you enter a room where an argument has recently taken place. Even if you haven't witnessed the conflict directly or received any explicit information about what occurred, you often sense immediately that something is wrong. The emotional atmosphere seems to linger in the space, affecting your mood and behaviour in subtle but measurable ways. This isn't because emotions leave literal traces in the physical environment, but because human beings are extraordinarily sensitive to micro-expressions, posture, vocal tones, and other subtle cues that carry emotional information. This sensitivity to emotional fields extends far beyond face-to-face interactions to encompass larger social and cultural patterns. Collective moods seem to emerge from the interaction of individual emotional states in ways that create emergent properties not reducible to their components. The feeling of a crowd at a concert, the atmosphere of a city during a celebration or crisis, the emotional climate of an organisation or community all represent field-like phenomena where individual contributions combine to create something larger than their sum. The random fluctuations in space-time that we've been exploring might offer a metaphor for understanding how these emotional fields propagate and influence individual experience. Just as gravitational noise could introduce unpredictable elements into physical measurements, the complex dynamics of emotional contagion and resonance might create effects that appear to transcend normal causal boundaries without actually violating any physical laws. Some interpretations suggest, though this remains unproven, that consciousness itself might exhibit subtle or non-local correlations similar to quantum entanglement, allowing for experiences of connection that cannot be explained through conventional communication channels. While such ideas lack scientific consensus and should be approached with appropriate skepticism, they point to experiences of connection and synchronicity that many people report, but that current scientific paradigms struggle to explain adequately. Take a moment to reflect on your own experience of emotional connection and influence. Have you ever felt your mood shift in response to someone else's emotional state without any obvious communication of that information? Have you experienced moments of seemingly telepathic connection where you and another person shared thoughts or feelings in ways that seem to transcend normal sensory channels? These experiences might not involve literal quantum entanglement or field effects, but they do suggest that the boundaries between self and other, between individual consciousness and collective awareness, are more permeable than strictly individualistic worldviews assume. Consciousness might be less like a spotlight illuminating an independent reality, and more like a node in a vast network of relationships that extends far beyond the boundaries of individual brains. One of the most mysterious aspects of conscious experience is the phenomenon of recognition, the immediate knowing that accompanies encounter with truth, beauty, or deep meaning. When you hear a piece of music that moves you profoundly, read a poem that captures something you've never been able to articulate, or grasp a scientific concept that suddenly makes sense of previously confusing observations, there's often a quality of recognition that feels like remembering something you had temporarily forgotten rather than learning something entirely new. This recognition response might reflect consciousness's natural resonance with patterns of organisation and relationship that extend far beyond individual experience. Just as tuning forks vibrate sympathetically when exposed to frequencies that match their natural resonant frequency, awareness might be naturally attuned to detect certain kinds of order, beauty, and meaning that reflect deeper structural principles governing both mind and cosmos. The mathematical elegance that physicists find so compelling in theories like quantum mechanics and general relativity might represent this kind of resonant recognition. When Einstein described his criteria for evaluating scientific theories, he emphasized not just empirical adequacy, but also aesthetic qualities like simplicity, elegance, and mathematical beauty. These aesthetic judgments don't seem to be arbitrary personal preferences, but responses to objective features of reality that consciousness is somehow equipped to detect and appreciate. This suggests that the appreciation of beauty and truth might not be merely subjective experiences, but ways that consciousness participates in recognizing the deeper patterns that organize both physical reality and mental experience. The random fluctuations in space-time that might make gravity fundamentally uncertain don't eliminate these patterns, but create space within deterministic structures for the kind of creative emergence that generates novelty while preserving underlying harmonies. Consider your own experience of recognizing truth or beauty. When you encounter something that strikes you as profoundly meaningful, there's often a quality of inevitability, as if this particular configuration of elements was somehow destined to exist and you were destined to recognize it. This feeling of recognition suggests that consciousness might be naturally aligned with the creative principles that generate complexity, beauty, and meaning throughout the cosmos. This alignment doesn't require any mystical or supernatural mechanisms, just the recognition that consciousness evolved within the same physical reality that it seeks to understand. The patterns that organize neural networks, the principles that govern information processing, and the dynamics that generate creative insights all emerge from the same fundamental forces that shape galaxies, atoms, and potentially the random fluctuations of space-time itself. As you reflect on moments of deep recognition in your own experience, notice how they often involve a quality of surrender, a letting go of effortful seeking that allows something already present to reveal itself. This receptive quality of consciousness might mirror the way that quantum measurements select one outcome from among many possibilities, not through force or manipulation, but through a kind of gentle focusing that allows potentiality to crystallize into actuality. As we reach the end of this strange and winding journey, through the possibility that gravity itself might be random rather than quantum, we find ourselves standing at the edge of a profound mystery that may never be fully resolved. The evidence we've explored, from the betting war between brilliant physicists to the silent testimony of neutrinos travelling billions of years through empty space, suggests that our universe might be far more chaotic and fundamentally unpredictable than we ever dared imagine. Whether Oppenheim's theory proves correct or falls to experimental refutation, the questions it raises will linger long after the measurements are complete. We've discovered that even our most basic assumptions about the permanence of information, the predictability of mass, and the unity of physical laws might be built on foundations as shifting and uncertain as the space-time fluctuations we've contemplated. Perhaps that's the most profound lesson of all. In a cosmos where even gravity might dance to random rhythms, where black holes could, in principle, erase the very record of existence, and where the weight of objects may subtly fluctuate with the restless energy of space itself, we learn that uncertainty is not a flaw to be corrected, but a feature that makes reality perpetually creative, eternally surprising, and infinitely more mysterious than our boldest theories suggest. You're creating everyone's reality, and they're rewriting yours. 2 explores how these cosmic principles of uncertainty and interconnection manifest in the intimate realm of human consciousness and social reality, where individual minds shape collective experience in ways that mirror the quantum entanglements we've discovered.